Let's solve the problem of the day. Well, the problem is array to binary search tree. Okay, and here the problem statement says that given a sorted array, convert it into a height balanced binary search tree. Okay, and return the root of the BST. Quite simple. Now it is saying a few more things, that height balanced tree means a binary tree in which the depth of the left subtree and the right subtree for every node never differ by more than 1. So now what you have to keep in mind is the tree that you're designing, it should not go imbalanced. We have already, like, if you have studied AVL trees, then you must remember, then the difference must be out of this like these three numbers, or you can say difference should belong to this set, right? Okay, one note is given here. It says the driver code will check the BST, and if it is height balanced or not, the output will be true, otherwise output will be false. We have to just keep in mind that we have to create a tree and we have to return the root of it. This will be taken care by the driver code. Let's take a few examples of it. So here you can see these are the sample test cases. In this one, you're given this array. Okay. Accordingly, we are creating this binary search tree, and you can check that it is completely height balanced. Let's check it for 4. You can see it has 0 height from here, 0 height from here. Thus, it has, if you want to consider it 1, it will be of 1 height, but that wouldn't go imbalanced, right? Its height would be 1, but the balancing factor is going to be 0. It is balanced. Checking 3. This side, this height will be 1, this height will be 0. The difference would again be 1, which is considerable. Checking for this one, right? This side the height would be 1, this side the height would be 0. Difference is 1, considerable. Checking for 2. This side the height would be 2. This side it would be 1. Again, we perform the difference. The difference is going to be 1, which is considerable. That means this tree that we have created is going to be the answer. All right. Now here, this happens with this same input. Okay, we create a binary search tree out of it, and we make sure that it is height balanced. Okay, let's talk about the concept a little. What happens when we create a binary search tree? Let me just put random numbers here. If I have to create a binary search tree out of this given data, what usually I do? I begin from here, right? I consider this as my root node. Let's make it correct. I go to the next element. I see 56, correct? I know the property of binary search tree, all the bigger elements on the right side, all the smaller elements on the left side. So I went towards the right, and here you can see null was encountered. So the moment I encounter null, that means that is the place I want to add my new node at. Here I added 56. Fine. Then I encounter 34. 21, 34 is going to be bigger than that. I come here. I see 56. 56 is going to be bigger value than 34. Correct? What do? I go towards the left side. I went towards the left. Here I encountered null. The moment I encounter null, that means here is the position I want to put my new node at. Going on to 16 is smaller than 21. I encountered null. I put 16 here. I saw 14. Again, I put 14 here. Smaller than 21, smaller than 16. Correct? This is how we make a normal binary search tree. Every node that we are inserting is going to be taking approximately log n amount of time. Now, if we have to perform that operation n times, that would result in n log n. But we also have to keep in mind that we are making this tree height balanced. And if we are making height balanced tree, that means we are talking about, let's say, AVL trees, the most general ones. And there, what do we have to do? The moment the tree goes imbalanced, we perform rotations, correct? And those rotations, usually it will cost O1 time, but if we have to perform it multiple times, now you have to keep in mind, the question says the array that we are given is sorted. Now, if we are performing these operations in a sorted array, it is going to be worst case, okay? And you are going to be performing multiple times rotation, fine? You already are using n log n, and then the overhead is going to be of your rotations. So it is for sure that we are not going to be using this approach, because the question demands the answer in O of n time complexity, right? So all of this is not going to be used in this particular question. Then what do? Observe the question carefully. The question says that the array that we are being given is sorted. So we must make use of it, right? So the property of array being sorted is going to come handy in this particular case. Remember, what do we do when we perform binary search? We go to the middle of the element, right? Now the middle element ensures that all of the values that are present on the left side of it are smaller, and all of the values that are present on the right side of it are bigger, correct? Let's take a similar approach while we are constructing this tree. Okay, let me try to create a recursive formula, or you can say a recursive function, in which what do I do is I take this big problem, I find out the middle point of it, and I will create it as root. Then the right subproblem that I have is going to be constructing my right subtree. The left problem I have is going to be constructing my left subtree. And because we are distributing like same number of children, approximately same number of children towards left and right, we do not have to take care about balancing explicitly. It would already be balanced because we are distributing the children evenly. Now the subproblem will be enacting just like the problem that I have, like the primary problem. This would be, in this I would be considering the middle element. The left side is going to be comprising of the left subtree, and this would be comprising of the right subtree, and the root will come here as 2, right? Same is going to be happening in this direction here. So I just have to design a function in which I find the middle element, and I call upon the left subtree for I call upon the recursive call for the left subtree and then for the right subtree, and the distribution is going to be happening similar to binary search. Okay, let's try to see the code of it. So you can take a look. This is my function. I have just made a utility function. What am I passing in it? I'm passing the array, and I'm passing the leftmost and the rightmost pointer for like in my array, which is going to be 0 and n minus 1, or you can say the length minus 1 initially. And once that is received in this function, I do have to perform a check that my left is always on left side of the right. If it exceeds, that means that is my base condition, and at that point I'm going to return none. I just have to find the middle with this simple formula, and then what will I do? I will create a new node. I'll create a new node. I will treat that as a root, and for that root I have to generate the left subtree. So I said node.left equals this function. Nums is being passed here. Left, that means the left boundary. Middle minus 1. If this is the middle, let's consider this to be the middle minus 1. From here to here, this is my left subproblem. And that, once the tree is created, its root is going to be returned. And I'm going to keep that root here at nodes left, at current roots left. Fine. Same thing is going to be done with the right side. I'm just taking nums, middle plus 1, this point, till right, till the last node. So this is going to be the right subproblem. I will call this function upon it. The same use is going to be here. It will return, like it will generate the tree and it will return me the root of it. I'll keep that root at node.right. Okay. Once this recursive function has successfully run, this call would be returning the primary root of this complete array that we have created now into a binary search tree, and then it would be returned to the main function, and then the background code will check that if it is a perfectly balanced tree or not, and if it is for sure binary search tree or not. If it follows both of the conditions, your answer is going to be true. Okay. Now what complexity is it taking? Well, if you talk about the time complexity, it is O of n, because we are just traversing the array once. Okay. We are going to each and every element, and we are not performing the usual binary search pattern in which we have to look for a path. Okay. We are not performing that. We're just going through the array, and we already know what would be the suitable position for this root. So we don't have to find it in the binary search tree. Log operation is no need here. So final time complexity is going to be order of n. If I talk about the space complexity, again, we are creating n nodes for n different values, right? So the order of n is going to be the space complexity. Also, once you are using a recursive function, if you want to consider the recursive stack, it is going to be at most log n, not more than that. So in front of this exponent, it is going to be negligible. So eventually, these are our complexities. Let's try to run our code and see if it is passing for all the test cases or not. So here is the same code that I've just shown you. Let's try to compile and run it. Okay. So for this sample test case, it is giving us the expected output. Let's try to submit that and see if it is passing for all the other test cases. All right, so it has passed for all the test cases. I hope you have got this particular solution. And if you again have any sort of problem, you must rewatch this video. If you like the solution, then please tell me in the comments and do like the video. Thank you.